Hi, I'm Ron Major, Senior Scientist at Agilent Technologies. I'm here with Bill Champion, one of our applications chemists in the HPLC Tech Support Group. Today we're going to continue our series on LC troubleshooting. Today we're going to talk about ghost peaks. We have several names for these peaks besides ghosts, such as artifacts, anomalies, or spurious peaks. These terms all mean that there are peaks in the chromatogram that don't actually represent the composition of your sample. Ghost peaks can come from a variety of areas: contamination in the LC system, contamination in the mobile phase, or even contamination from our own sample. We'll discuss how to identify the source and how to correct or remedy it.
You know, Ron, I often talk to chromatographers who see peaks they believe should not be in their chromatograms. Determining the source and how to remove these artifacts can be challenging and frustrating. As Ron said, these peaks can come from the LC, from the mobile phase, and from sample preparation. We'll talk about these in order. First, elution of analytes retained from previous injection. This is easy to diagnose and fix. This is a simple chromatography problem. Next is mobile phase contamination. This is a little more confusing and a little more difficult to diagnose, but it also is easy to correct. Sample preparation. This can be insidious and difficult to diagnose. It can be a chemistry problem. Fourth is system contamination. For modern instruments, this is typically not the source of ghost peaks, but we will briefly discuss some ways to determine if the ghost peak is coming from the instrument. And finally, we'll talk about column contamination. The column is almost never the source of ghost peaks, but the column is often blamed for being the source. Column contamination is an important problem, but the contamination of the column more often affects column pressure, peak shape, and possibly sample recovery. It's almost always caused by poor sample cleanup. This is an example of an injection of chlorpheniramine. Chlorpheniramine is an antihistamine. I like this example because it actually demonstrates several concepts. Chlorpheniramine maleate is a salt of maleic acid and chlorpheniramine. As an aside, when we have samples that are salts, we typically see two peaks. One peak is from the acid and one, in this case, maleic acid, and the other is from the base, in this case, chlorpheniramine. In solution, the salt dissociates and the acid and the base typically move down the column separately. The chromatographer running this analysis initially thought that she had coelution of chlorpheniramine and maleate, which, as I just mentioned, is not likely. She did another injection, adding pseudoephedrine, and obtained the results on the right. This is very confusing. She added a single component and got two extra peaks.
Here's what really happened. Since we're running out of basic additions, pH 11, the first peak is maleate in the ionized form. The second peak is the pseudoephedrine, and after leaving the instrument running for a while, a third peak is also observed. The third peak is actually chlorpheniramine from the first injection, believe it or not. Because chlorpheniramine is more lipophilic and thus more retained than malic acid or pseudoephedrine, and because the initial runtime was awful short, 7 minutes, chlorpheniramine did not elute until more than 15 minutes after the initial injection. A peak that shows up in the next chromatogram is sometimes called a wraparound peak, because the peak is wrapped around from the previous injection. If the user had let the chromatogram run for 20 minutes or so, a second chlorpheniramine peak would have been observed. In method development, we often use a fast gradient, such as 10% to 90% acetonitrile, in 10 or 15 minutes to get the feel for the number of components in the sample and their relative retention. We'll discuss gradients in another video. But even with isocratic separations, we should always start with this very strong mobile phase. For example, in this case, maybe 75% methanol or even higher, and also use a higher flow rate to get components to come off the column in a more reasonable amount of time. For a 150 millimeter, 5 micron column, we should be able to use a flow rate of around 2 mils a minute. Another clue that this is a wraparound peak is that it's much broader than the peaks that elute near it. In isocratic work, one almost never finds a broad peak so close in proximity to a narrow peak, such as the pseudoephedrine peak in the figure. Since the theoretical plates are proportional to the square of the ratio of retention time and peak width, if the calculated theoretical plates for a peak is reasonably low, it could be indicative of a wraparound peak. Or more simply stated, the peak width is proportional to the retention time. So unusually broad peaks are likely wraparound peaks. The fix for wraparound peaks is easy. For isocratic work, you can increase runtime, you can increase flow rate, you can increase the mobile phase strength, but it's much easier to run a gradient instead.
A little chemical intuition would also help solve this problem. The structures of these molecules are shown. Malleate is very ionic. It has very little retention in reverse phase chromatography. In fact, in this example, it comes out very close to the void volume. Pseudoephedrine should be less polar than malleate, but more polar than chlorphenyramine. So in reverse phase chromatography, the order of elution should be malleate, pseudoephedrine, and then chlorphenyramine.
Unfortunately, it's not always recognized how important it is to use high purity solvents in HPLC.
I sometimes get calls from chromatographers who have ghost peaks that they cannot get rid of. Often they believe that the ghost peaks are coming from contamination of the column or somewhere in the instrument. The symptoms are, even after extensive flushing, the contamination does not decrease in size. The peak or peaks show up only when a gradient is run, and the peak or peaks show up even when the gradient is run without making an injection, and the peaks do not decrease in size with subsequent injections. It's often difficult to convince people that the problem is in the mobile phase and not something stuck on the column. It's often necessary to lay out some experiments to prove the problem is really mobile phase related. I know I didn't believe it the first time I was confronted with a mobile phase contamination problem.
Here's what's really happening. The mobile phase contains an impurity, or possibly impurities, that has some retention in the stationary phase. That means that with the initial mobile phase strength, say 25% acetonitrile, there's an equilibrium concentration of the impurity in the mobile phase and in the stationary phase. After equilibrium is established, if you then run a gradient, the equilibrium is shifted to increase the relative concentration in the mobile phase. That means the impurity will come out as a band, and often it will look like a peak or a series of peaks. There are several ways to demonstrate that this is from the mobile phase. The contamination can be in the mobile phase additives, such as TFA, formic acid, or in the buffers. So run a gradient without any of these additives present. The contamination may be in the water. Sometimes people use purified water, but not HPLC water. So try HPLC grade water, either from an in-house purification system or from a bottled HPLC grade water. Note that the purification performance of in-house water systems are monitored based on conductivity and not on UV absorbance. Conductivity is a measure of ionic purity, but not of UV purity. In your in-house purification system, it may be necessary to change the activated charcoal filters more often. Some users prefer purified water by using an old reverse phase prep column, and this will remove hydrophobic contaminants from water that has passed through it. You can change water sources and see if that ghost peaks are eliminated or changed. This chromatogram shows a difference on baseline from different sources of water.
It's also possible that the contamination is in the organic solvent. So again, use fresh HPLC grade solvent, possibly even from a different manufacturer. This chromatogram shows the background response from different sources of acetonitrile. Note in the lower chromatogram the absence of small peaks present in the upper trace. Another approach, if you're using acetonitrile, replace it with methanol or vice versa. A way to demonstrate that the ghost peaks are from the mobile phase is to vary the gradient. If you're not familiar with gradients, you may want to watch the segment we have on gradients. After the completion of a gradient, one must get the column back to the original mobile phase composition. This process is termed re-equilibration and can be accomplished by an instantaneous return to the initial composition or by a negative gradient, which is slower but sometimes more effective. Once you've returned to the initial composition, a brief time is required to stabilize the column and to get a steady baseline. This is termed the equilibration time. If there are impurities in your mobile phase, there's a possibility that these contaminants may build up at the head of the column out of the weak mobile phase during this equilibration time. The more equilibration time you have, the more time your contaminants have to build up on the column.
So let's look at a procedure you can use to determine if the contaminants are from your mobile phase. We can refer to the figure on screen to help explain this procedure. Here there are 3 blank chromatograms. In other words, no sample injected, but the gradient was run, each of which represents a different equilibration time. Note the drifting baseline, which is present on all 3 chromatograms. This drifting baseline may be due to impurities, but most likely it's a result of a change in absorbance due to the buffer system or a refractive index effect. We won't be concerned with this drift. What we are concerned about are the peaks showing up in the 5.5 to 6.2 minute time frame. These peaks could interfere with peaks of interest, and therefore we have to understand their source and figure out how to get rid of them. The bottom chromatogram, the blue one, represents the original gradient with its equilibration time of 10 minutes already established. One can see the evidence of 6 or so peaks with the respective peak heights or peak areas in the 5.5 to 6.2 minute time frame. So, to determine if the contaminants originating from the mobile phase, we add an extra 5 minutes of equilibration time for a total of 15 minutes. See the middle chromatogram, which is red. Note that the impurity peaks slightly increased in their peak height, also of course their peak areas. So next we ran an extra 10 minutes of equilibration, and as can be seen in the top blank chromatogram, the peak heights or the areas have increased even further. We can repeat this experiment to ensure that the blank chromatograms can be duplicated further, indicating that the buildup is reproducible, which it should be. This series of experiments showed that the impurities originated from some trace impurities in the mobile phase, building up with increase in equilibration time. From these results, however, we can not really tell if the impurities were present in which of the two mobile phase solvents, so each may have to be further investigated, as was discussed earlier.
I have a brief comment about mobile phase additives, such as buffers or acids. Some additives, such as trifluoroacetic acid, TFA, can contribute to background absorbance and also be a source of impurities. We recommend using high-purity TFA. Several companies sell high-purity TFA in ampules. These are often higher purity in part because the TFA is not exposed to air. One other issue that is well established but not always well recognized is that the UV spectrum of TFA changes as the acetonitrile-water ratio changes. As the acetonitrile level is increased, the UV absorbance of TFA increases, and this gives a baseline rise. Sometimes people use TFA in the aqueous mobile phase solvent and TFA at a lower concentration in the organic mobile phase solvent. For example, if you use 0.1% TFA in water, use 0.086% TFA in the acetonitrile. These percentages balance out as the gradient drift and gives a more stable baseline. Another way to reduce the TFA background response is to use a longer wavelength, for example, 235 nanometers, 254 nanometers, 280 nanometers, etc., where TFA has poorer absorbance.
Good column hygiene is important to prolong the lifetime of an HPLC column. A column used for analysis of clean samples should last for 1,000 or more injections. An HPLC column used for dirty samples, such as plasma, urine, or other biological fluids, environmental samples, or other samples with messy matrices, may last only a few tens of injections or less without good sample cleanup. Use sample cleanup, such as solid phase extraction, also called SPE, liquid-liquid extraction, or protein precipitation before injection. You can also use a simple filter, such as a mini Uniprep filter. Filtering your sample prevents the blocking of capillaries, frits, and the column inlet. But the filter removes only particulates. It does not remove dissolved contaminants. Interestingly, there is sometimes confusion about that. The porosity of a typical membrane filler is 0.45 microns. This pore size is much, much larger than any molecule that you encounter. So that's why we use something like SPE or liquid-liquid extraction to remove possible contaminants based on their chemical and physical properties. We often see problems with columns used for biological fluids. There are components like proteins which can stick very tenaciously to the top of a reverse phase column. People often try to crash proteins by shaking the biofluid with acidified acetonitrile, followed by filtration or centrifugation. That sometimes works, but the filtrate still is not very clean. Thus, the column lifetime is less than for clean samples. We'll talk more about sample prep and column flushing in other videos.
However, we do want to talk about ghost peaks that actually come about as a result of sample preparation. There can be many sources of contamination from samples. There can be impurities in the sample solvent. There can be impurities in the components added during sample preparation, such as buffers or internal standard. And there can be degradation of the sample or impurities in the autosampler vial on standing. So at a minimum, you should inject the sample solvent to ensure that there is nothing in the sample solvent that contributes to spurious or ghost peaks. So typically we make an injection of the sample solvent. In addition, take a blank through the sample preparation protocol such as filtration, extraction, addition of internal standard, etc. Also, it's a good idea to make blank injections during the course of multiple runs to demonstrate there are no ghost peaks present due to carryover. The analyte or components in the sample can degrade and cause spurious peaks. If the degradation does not occur instantly in the sample solvent, you can often isolate this by re-injecting the same sample over the period of several hours or even the next day. Let's talk about system contamination. One likely place to have system contamination is in the autosampler. This is especially true when using high sensitivity LC-MS and LC-MS-MS. In modern instruments, there are often programmable steps in the autosampler sequence to reduce or eliminate carryover. Here we have a schematic of a typical modern autosampler. Common areas where contamination can occur in the autosampler are in the autosampler needle, the switching valve, or the sample loop. A feature of newer instruments is an automatic needle wash that can be used to rinse off the outside of the needle.
We've talked about this consistently in our troubleshooting videos. Identifying the source of an issue is often the most time-consuming part of troubleshooting. Here's one tip to help you quickly begin to identify the source. Disconnect your column from the instrument and replace it with a narrow piece of capillary tubing, say 0.12 millimeter ID, and then make a blank run. If your ghost peak still appears, then you likely have a system contamination issue. You can work backwards through the key system components, such as the column inlet or the autosampler. When you eliminate the ghost peaks, then you can focus on that component as your source.
We can also remove the autosampler source of ghost peaks by making a run without any involvement of the autosampler. We sometimes call this a blank gradient. That is, we start the gradient without any action by the autosampler, including there's no valve switching. With ChemStation, if you do not set a vial location in the sequence table, the entire autosampler operation is skipped. If the ghost peaks don't show up, they may be coming from the sample, or they may be sample solvent related, or they may be due to autosampler contamination. If they're still present and do not decrease in size, they're likely to be in the mobile phase.
There are several means to clean the column. As we've previously discussed, many of the problems that are blamed on the column come from other sources. However, contamination by poor sample cleanup can be the cause of column fouling or chromatography problems. Before we move to column cleanup, I'd like to comment about contaminants hiding on a column. The LC column is fully packed with particles. The column is well swept by mobile phase. There are no dead spots or other hiding places for contaminants. Column manufacturers work very hard to ensure that there are no dead volumes in the column. If there were dead volumes, they would contribute to extra column band broadening or give tailing peaks. So, if we flush the column, we should not expect ghost peaks to appear from contamination that had been hiding on the column. One of the things you should try to do if you think you have a contamination from previous injections is to backflush your column. I discussed this process pretty thoroughly in the segment we did on pressure changes. When you clean your column, wash with a solvent that is stronger than your mobile phase. It's a good idea to take your detector out of the flow path before rinsing. First, assuming you are using reverse phase column, you'll want to wash your column with a mobile phase without any of the buffer salts present. Then, wash with 100% organic. Typically, if you're using methanol, you would start with methanol and move to acetonitrile. If you're already using acetonitrile, you might use methanol as the second wash solvent. Methanol may provide a different solubility than acetonitrile. After you've done this, check your column to see if the pressure has returned to normal. If not, either discard your column or consider more drastic conditions. An easy thing to shift to is a mix of 75% acetonitrile and 25% isopropanol or IPA. The IPA is a stronger solvent for removing material, but it has a higher back pressure. If you already have a high back pressure to begin with, you do not want to start with 100% IPA directly. It will also be necessary to use lower flow rates so you don't exceed the system pressure. After you've used the acetonitrile IPA mixture, go to 100% IPA. If 100% does the trick, stop there. If it doesn't solve the issue, then look for stronger nonpolar solvents like methylene chloride or hexane. It's important to use isopropanol prior to the use of these stronger solvents, as well as be returning to the acetonitrile solvent, mainly for miscibility reasons.
Okay, so let's summarize. Ghost peaks can come from a number of sources. They can be an elution of analytes from a previous injection, or wraparound peaks as we call them. If you're using an isocratic method, you can increase your runtime, increase your flow rate, or increase your mobile phase strength to take care of them. You can also use a gradient.
You may be getting ghost peaks due to mobile phase contamination. Be sure to use HPLC grade solvents so that you reduce mobile phase related peaks. Consider your sample preparation also. Make sure you don't introduce contaminants in your sample prep steps.
System contamination, specifically in the autosampler, is another place to look. Start by bypassing the autosampler and running a blank gradient to try to isolate the source of ghost peaks.
Lastly, consider the column. The column is almost never the source of ghost peaks. However, there can be other chromatographic issues related to column fouling, such as poor peak shape and increased column pressure. So cleaning your column is a useful process.
Determining the source of ghost peaks can be very difficult. So as always, if you've tried to troubleshoot your issue without success, you can always contact Agilent Technical Support for assistance. You can find your tech support contact on the agilent.com website. Thank you.